Okay, so now we have covered the Bernoulli distribution, okay, where we have two outcomes, okay, and then we only do a single trial, and we define that as a Bernoulli distribution with success probability P. We wrote out its PMF, and we also derived its mean and variance. So building on that, a very popular, commonly used distribution is what we call the binomial distribution. So the name, again, remember the binomial theorem and stuff like that we did before? It's related, okay? So let's see how they're related by starting with a definition. So we define X, okay, to be the number of successes, okay, in a fixed number n of independent trials with the same success probability P as having a binomial distribution. So it sounds a little bit complicated. Okay, so let me try to break it down for you a little bit. Notice that all of the underlined clauses, they're pretty important, okay? So each trial is a Bernoulli trial, actually, okay? But then each, like Bernoulli is defined for a single trial, so we're actually looking at in like a series or sequence of independent Bernoulli trials, okay? So that's why, like, one thing we need to keep in mind is that they're independent, okay? That's a keyword, okay? And we also say that we're doing a fixed number of independent trials, okay? So like N is the number of Bernoulli trials that we do, okay? And it's fixed. We need to know it beforehand. It's not like changing or anything, okay? And also notice that for all of the independent Bernoulli trials, they all have the same probability of success. Okay, so all of them are independent Bernoulli trial with the same success probability. Okay, lastly, okay, just to keep in mind, the random variable itself, the X, is defined to be the number of successes out of n trials. Okay, so we highlight all of those clauses down here with the underline. So keep in mind that all of this needs to be satisfied in order to have a binomial distribution. All right, so with that in mind, okay, since we're working with a random variable, in this case, a discrete random variable, so we should be able to try to write out its PMF, okay? The PMF of it, okay, is that if we're looking at the probability of X equals to K, okay, so K, of course, going to be between 0 and N, okay, because N is the total number of trials that we're able to do, and 0 is the lower bound, right? And it's the number of successes. So K will have to be between 0 and N, and it has to be integer, okay? So when we define that, this is saying that the PMF of X is of X equals to small k is the probability of getting K successes in N trials. Okay, so before showing the PMF directly, okay, let's think about how we can actually get that PMF. I think all of the stuff that we need to know actually is already available. Okay, so now we just need to put all of the pieces together. And this is actually going back to chapter 1 about combination. Okay, so we need to get K successes in N trials. Okay, this is very similar, if you recall, about when we're trying to use a combinatorial analysis to show why the binomial theorem works. Remember? We're trying to figure out, like, say, if we're able to come up with a license plate with like 26 possible uses of the letter and then 10 possible uses of the, I think, numbers. And then we're saying that how many distinct license plates, right, of length n that you're able to get with exactly K, say, K number of letters. Okay, so this is getting similar over there. Okay, so let's see. So for N trials, okay, all of them have the same success probability P. Okay, they're independent. Okay, and if I want to find the probability of getting exactly K successes in N trials, okay, so for me, I need to first of all figure out where exactly I'm going to have those K successes out of N trials. Okay, so we do an N choose K, okay, to figure out among the N trials, which K are having the success. Okay, so once we determine that, we need to multiply with the probability, right, of getting those successes. So the success probability is P, and we're getting K successes. They're all independent, so we raise it to the power of K. Okay, but don't forget that the remaining, okay, N minus K, they all need to be failures. So we also need to multiply with 1 minus P as the failure probability raised to the power N minus K. So this, like I said, looks very similar to the binomial theorem before, right? Whereas there A and B, they're just number of cases, number of possible outcomes that you're able to do. whereas here P and 1 minus P, they're probabilities, okay? So with all this in mind, let me just show you the PMF itself, okay? So we write X tilde, okay? BIN stands for binomial. There are two parameters. N has to be fixed. That's the number of trials, okay? And then P is the success probability. So we need both two to determine what a binomial distribution, this random variable is, okay? So just like what we did earlier, PK, which is the PMF at K, okay? And again, K is integer, lower bound 0, upper bound N, okay? And then the PMF, the probability itself, is N choose K times P to the power of K, and then 1 minus P to the power of N minus K. Alrighty, so with this in mind, let's look at a few examples of binomial distributions, okay? So remember, for Bernoulli, we're only considering single trial. Okay, now for binomial, we're considering a sequence of fixed number of N trials that are independent, and then we care about the number of success, okay? So if I'm looking at, oh, by the way, and also they have to have the same probability of success P for each trial. So the first example here, the number of heads obtained by tossing a fair coin 10 times. Okay, so it's going to be a binomial distribution. Okay, X, okay. And then N is 10, because that's the number of the fixed number of trials. And then P, success probability, is 0.5, because we're working with a fair coin. Okay, so the second example follows what we had earlier with the Bernoulli as well. If I'm looking at the number of 6 obtained when rolling four fair 6-sided dice simultaneously, then the number of successes, okay, gonna follow a binomial distribution with N to be 4, because I'm rolling 4 die and 4 dice, and then success probability, because again, there are fair 6-sided dice, so we have 1/6, okay, as the success probability. Okay, the last one, okay, the number of A's students were earning this semester. Okay, or I'm just talking about like one particular student, let's just say. Okay, so N is the number of classes you're taking. P, if we're defining this as the probability of getting an A, probably varies by classes. Okay, this example actually is a counterexample of not a binomial random variable. Okay, so the thing is, N is the number of classes you're taking. It could be fixed for a particular student, of course, but then because P, okay, varies by classes, so we violate like this, because it's not the same probability of success, okay? And also, I would also mention that the different classes, like getting an A, probably are not so much independent from each other. Let's just say if you're taking 2 math and stats courses this semester, the grades you're getting probably are related, just like reflecting, like say, the effort you're putting in and things like that for those courses, okay? So they're not independent and probably do not have the same success probability. So this is not a example of binomial distribution. All right, so with all this in mind, let's try to figure out how we can find a PMF, okay, of a binomial random variable. Okay, so X is the number of 6 obtained when you roll 4 fair 6-sided dice simultaneously. Okay, so that goes back to what we just talked about, one of the examples. Okay, all right, so we started off with N equals to 4. Okay, P equals to 1/6. Okay, so we know that the PMF, okay, generically we're writing as PK equals to N choose K times P to the power of K, and then 1 minus P to the power of N minus K, and K is anything between 0 and 4 taking an integer value. Okay, so the question asks you to find the PMF. Okay, so what that means is that we wanted to show P0, P1, P2, P3, P4, one by one. Okay, so the rest will be a overall straightforward algebra question now. Okay, so P0, okay, is 4 choose 0 times 1/6 to the power of 0, and then 5/6 to the power of 4. Okay, you can leave it like that, but I'm showing you the probability over here as well. Okay, and we do that for 1. Do that for 2, do that for 3, and then do that for 4. Okay, and the one reason why I show this up in this, not only just the choose function with just like the PK value, PK expression, but also the values, is that like if you're able to do this, like adding really quickly, maybe using a calculator, you will see that all of this should add up to 1. Okay. So this is not surprising, okay, because K, or I should say X, capital X, the random variable, can only take one of the 5 values over here. Okay, so we're having a partition, okay, and then they're disjoint as well, right? And then we have exhausted the entire sample space. So by, I think, one of the axioms that we have covered about the probability, sum 1, we know that they should add up to 1, okay? And also, I'm just going to show you on a graph of how the PMF looks. Okay, so clearly, I guess the highest, well, from the numbers, we see that as well. But once we graph it into a bar graph, like what we're showing over here, we can kind of see that this is a decreasing PMF function, starting like the highest probability is at P0, and then the smallest is at 4. Okay, regardless, they're going to add up to 1. All right, let me talk about one more example just to highlight how important it is to check the conditions when you're using the binomial distribution result, okay? Suppose 42 of the students in the class have part-time jobs. Among a random sample of 10 students in that class, what is the probability that exactly 8 are gonna have part-time jobs? Okay, so n equals to 10, okay? P is 42%, okay? So what we need to do is to actually just use the PMF result of the binomial probability, binomial distribution, right? We need to find Px equals to 8, okay? And then we know that, sorry, my pen, for some reason, is not working the greatest. Let me just, okay, equals to, I don't know, let me see, Px equals to 8, okay? So that's what we need to do. And then now we know we just need to sort of like use the binomial PMF result and then use K equals to 8 in this case, and then compute the probability, which once you do that, it's gonna be about 1.5%. Okay, so the probability that exactly 8 students out of this random sample of 10 students have part-time jobs gonna be about 1.5%. Okay, so for this one, I just wanted to highlight, like say, yeah, we are using the binomial result directly, but I wanted to walk us through to make sure that we can actually use the binomial distribution. Okay, so just to go over, remember like the 4 important results or like the 4 important conditions when we're using the binomial theorem. Okay, so remember, the trials need to be independent. Okay, so here the question is saying that we're doing a random sample. Okay, so that is generally saying that the selected observations are independent from each other. Okay, so that probably is satisfied. Okay, B, the number of trials n is fixed. So for us, because we're looking at the number of part-time jobs, like students, the number of students out of 10 students having part-time jobs. So n is 10 in this case, and it is indeed fixed for this particular question. Okay. The third condition, each trial outcome can be classified as a success or a failure. Okay, so again, we call them success and failure, but you can also say yes or no, 1 or 0. So for us, we're defining a success as having part-time jobs. Okay, so again, you don't see me now, but I'm using like quotes success, really like it doesn't really mean the literary meaning. We're really just talking about the question itself. So having a part-time job, if we define it as success, then indeed for each student, it's either an outcome of success or failure. Okay, so we are able to satisfy, I think, this third condition as well. The fourth one is, okay, the probability of success P is the same for each trial. Okay, so again, the question starts with saying that suppose 42% of the students in the class have part-time jobs. Okay, so if you randomly select a student, the chance that that student has a part-time job is 42%. Okay, and yeah, so in that case, I think all of this are satisfied. So we're able to use the binomial result to show, do this calculation specifically, but I would say that every time before we're doing that, we should make sure that all of the 4 conditions are satisfied in order to use the binomial result. Okay. Lastly, I wanted to show you one more thing. Okay, is that the PMF, if I'm able to graph it out, okay, of the binomial distribution, it's gonna be unimodal. Okay, what we mean by that is that you're only gonna have one mode, which is that if you look at all of the graph, the 4 different graphs over here, you only have one that is the tallest. Okay, the tallest in this case is the outcome that is most likely. Okay, because if you remember, what we're plotting over here is the PMF. Okay, it's the probability of taking that value. Okay, so it's going to be unimodal, meaning that you only have one mode, and mode by definition is the number, the value, the outcome value that is having the highest probability. Okay, so here I'm experimenting with different n and different p, as you can see. Okay, but regardless how you're defining that p and n, you're always going to get a unimodal distribution. Of course, the mode could happen like a very small value, like the first one, but you could also happen at some middle value, right? Like even here is symmetric, right? And this one is symmetric as well. And I would just mention that the reason why they're symmetric, because the success probability is like 50%. Okay, so it's going to be centered at the middle point. Okay. All right.